actually don't know if they came. I gotta email Mr. Morton. I gotta email Mr. Morton real quick and tell him I didn't finish the calculation sheet. And ask for forgiveness. Ask for
My bowling ball comes
Thursday.
today, so I'm excited.
And if not, just take me out.
Yes, I know. Isn't that great?
Have you ever gotten a turkey before?
Am I what?
Have you ever gotten a turkey?
Are you sure?
Yeah.
Oh.
What's that? 3 strikes in a row.
I lost.
What's after that?
Wait, you were sick, right?
I don't know. That's as good as I've ever done.
Are you normal?
That's good that you're back. Subject
Our
versus
first
subject.
bowling match is in December.
Late,
About-
late work.
Who's the bowling coach now?
Coach Chicas, and then like Coach Bryant. I think he works at the bowling center. But Coach
Is this a school-sponsored
It
thing?
is, yeah. The one guy works here. His last name is CHICAS. I think he's a soccer coach.
And I couldn't figure out a costume, so I just wanted to kick off like black.
Our bowling jerseys are very cool.
Well, like 3 people came in, they had my jerseys and they brought
You
me,
get
like,
jerseys?
and
I guess it's like a shirt.
I was like, that's so good.
Yes. Yeah, I saw that. Did they tell you that? Yeah. She wants to do that. I think that'd be really funny.
I thought she didn't make a team, but they just ended up putting everyone on.
Oh, I see, you're like a nerd.
It's Brady.
What is this on Friday? Or like what papers? It is manager. What P2? I guess so.
Yeah, people are just like, I guess.
Okay, you do. Also, did you try out though?
Wasn't 52
I don't know. It was contest.
I'm like, 54.
Why do you know how I said that?
53 and 22. 52 is, oh, 52 is. So if you get, yeah.
She showed me yesterday.
You turn that on Google Classroom?
Well,
Still,
51.
yeah. The percentage. She's not perfect.
Maybe if I told him yesterday.
Brendan, what does your shirt say?
It's try not to take that class.
Rocklahoma?
It's actually, if you want to have a fun,
Nice.
But it's really the worst. I don't like reading.
it's just so much fun.
The notes.
Is it a lot of reading? Or
Good morning, FHS. Happy Halloween. Today is Tuesday, October 31st, 2023. Would you please join me in a minute of silence? Please stand if you are able and join me in the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Thank you, everyone. Stay warm, happy Halloween, and have a great day.
All right. This morning we are going to start off with number 55, where we organize some of our information that we've been talking about, the differences between a function, first derivative, and second derivative. So nothing new there, just trying to organize that information to make it a little bit more manageable for us. Then I'll give you a chance to ask a couple questions from the circuit like I promised. I know all of those are worked out on the website except for like 3, I think, but I'm going to give you a chance to ask a few of those. And then we're going to spend the rest of class working on some practice FRQs. So 56 is the one that has 3 practice FRQs on the front and 2 practice FRQs on the back. So that's the plan today. So starting with 55, just kind of reviewing some of these topics and summarizing what they are, when you use them, when you would use the derivative versus the function versus the second derivative, and that kind of stuff. Okay, so critical numbers, what are they? Those are going to be numbers, and you're welcome to elaborate here, but numbers that make the first derivative equal 0 or undefined. So that's it. There's no other requirements to be a critical number. How do we find them? / where are they? Well, basically the same thing. You take the first derivative, set equal to 0. Also solve where it's undefined. So basically the same thing. What they are, where they come from is the same thing as how you find them. Okay, the when though, when would you want critical numbers? So obviously if the question's asking you for critical numbers, you would do this. But also critical numbers are good for finding increasing, decreasing intervals. And if they're good for finding increasing, decreasing intervals, indirectly they're good for finding relative and local min and maxes. So lots of reasons why you'd want to find a critical number, but maybe one of the most important things that we need to summarize are critical numbers are the only place a function may change direction. Critical numbers are the only place that a function might be changing directions. That's why it's important for increasing, decreasing, so that you know what numbers you need to test around to know when it's increasing or decreasing, and that way you don't have to test every x value, just the ones around the places where it might be changing directions. And then of course if you know increasing, decreasing intervals, the first derivative test uses critical numbers to help you find local maxes and mins. And finally, last thing we probably need to put down for critical numbers, the second derivative test also uses critical numbers in a different way, but it can also be used to find relative maxes and mins. So critical numbers get used for a lot of stuff. Most everything we do in this section. If it asks you to find critical numbers, you need to find critical numbers. If it wants you to find where the function's increasing, decreasing, you're going to need to find critical numbers to know what to test around. If you're trying to do the first derivative test, you need to be testing around the critical numbers to figure out where the maxes and mins are. Or you could use the second derivative test where you actually plug in those critical numbers into the second derivative. So all of that is the stuff we need to know about critical numbers. Anything else you think we should add, or anything you want me to repeat? Okay. Now, I think I'd mentioned this one in your notes, critical points, and I really need to put that in your notes, I guess, but what are they? They are just critical numbers that are also points on the function. So like x equals 3 could be a critical number if it makes the first derivative 0 or undefined. But if the function doesn't exist at x equals 3, you shouldn't call it a critical point. If it's not really a point on the function, if it's undefined there, it's still a critical number, but it's not a critical point. Alright, so critical numbers do all this stuff, and they focus around the first derivative. Inflection points has a lot of overlap. It sounds very similar to this, but the differences are very, very important. So inflection points are, well, they're points on the function that the concavity changes. Or where the concavity changes. So it's got to be a point, and the concavity needs to change. Okay, how do you go about finding them? Well, the candidates, or the possible inflection points, are when the second derivative equals 0, or the second derivative is undefined. That sounds just like critical numbers, but second derivative. But also, put that in capital letters because this one has an extra requirement. Not only does the second derivative have to be 0 or undefined, that's just the possible inflection points. You also have to have concavity change. So we have to do one of those sign charts, test the concavity to the left and right of each of those possible inflection points.
Isn't this one, the endpoints are also candidates?
Not for inflection points, no. That would be for absolute max and min values. Okay, so when would you want to find them? Well, I would be very surprised if your next test doesn't have one question that just flat out asks you to find inflection points. So of course, if it's asking you to find inflection points, you should be doing that. But also, you should be finding these if you're interested in when the function is concave up or down, upward or downward, because inflection points are where it's changing. So kind of like critical numbers tell you where the function might be changing direction, inflection points tell you where the function might be changing concavity. That way you don't have to test all the x values, you only have to test x values around the possible inflection points. Okay, so if you wanted to know concave up, concave down, if you were flat out asked if there were inflection points, and I guess one last thing would be within the second derivative test. Okay, never mind. That actually wouldn't be inflection points, but I guess that's all you need inflection points for. Okay, anything you think we should add? Anything you want me to clarify? Okay, then this is the part that I know is a little bit of a struggle right now, so this is why I really want to do this handout. If we plug in an x value into the function versus the first derivative versus the second derivative, we need to know, and again, we don't do applications of third derivatives. That doesn't mean that we won't ask you to do a third derivative someday, but functions, first derivative, and second derivative is about as extensive as Cal AB gets. So what a function does is it's going to tell you, if you plug in an x value into the function, that would give you a y value. So that would be good if you wanted to know a min value or a max value. And it helps you with points. If you need to know a point on the graph, or if the point exists, like inflection points has to be a point, so you need to make sure that the x value can plug into the function and not give you something undefined. Bless you. If there is a critical point, you would need to plug your critical number into the function and make sure that you plug it into the function, bless you, to make sure that it gives you a point. Okay, what happens when we plug in an x value into the derivative? Our first derivative. What does that give us?
Increasing and decreasing intervals.
Okay, so let's just say increasing, decreasing, or slope. In fact, maybe we should say, be a little more specific. Increasing when the first derivative is positive, and decreasing when the first derivative is negative. And when you need slope, first derivative just basically means slope. So if you need to know the rate of change of something, the instantaneous rate of change of something, the equation of the tangent line, all of that's the same thing. All that's wanting the slope at that instant. Okay, and then second derivative, what would it tell us? Well, it tells us that the function is concave downward when the second derivative is less than 0, concave upward when the second derivative is greater than 0, and that's about all the second derivative is going to do for you. Okay, so when would you do each of these? Well, it just depends on which of these things that you need. So if you needed a y value, you would plug into the function. If you needed a point on the function, or to know if it's a point, if you know what happens when you plug that in, then you know when you should be using it. Likewise, if you want to know when the function is increasing or decreasing, that's how you're supposed to know when to plug a number into the first derivative. Also, if you want to know slope, you would plug a number into the first derivative. If you want to know concave up or concave down, you're going to be plugging in the x value into the second derivative. So really knowing what these things do should also be telling you when you do them. Just depends on what you want. Okay, any of these you want to get a little more clarification on? Again, I'm just trying to summarize what the difference is between each of these, because that can be a challenge at this point. Okay, then let's move on. So second on our agenda is I'm going to let you guys ask a couple questions from the circuit, and then we will move on to the FRQs. So if you have no questions from the circuit, or as people ask questions from the circuit that you personally didn't need help with, go ahead and start one of those FRQs, and we'll look at some of those together here in just a bit. But again, I'm going to let you guys ask a few questions on this circuit, but most of these are worked out on the website, so I'm not going to take an unlimited number here, but I figured a couple might help out. Okay, so which ones from the circuit did you just have trouble starting? Didn't understand the question? Yes.
13. So that's the first one on the third page.
1, 2, 3. Is that this one? Okay. It's number 13. Okay, so quickly check and see if you have this numbered as 13. I don't know if this is number 13, but that's what sounds like other people are getting. And again, if you've already gotten this and you're comfortable with your answer, just start one of the FRQs to make the best use of your time here. Okay, so for this question, I need to know when is this guy concave down. So I'm going to have to figure out when his second derivative is negative. And when he is decreasing, which would be when the first derivative is negative. That's what that handout we just did, tried to organize some of this information, try to help summarize it to you in one nice, neat place. But what can be challenging about this question is you don't know how to take the derivative of an absolute value function. So really the only way to really do this mathematically, and you won't be on the hook for this, but you need to be able to change absolute value signs into a piecewise function. So I'm not going to get into that. We talked about that in pre-cal. But if you do that, then you can take the derivative of each piece individually. The reason why I'm not getting into that is because they don't expect you to do this on the AP exam. So we don't expect you to have to do it for us. But we can still answer this question because we can figure out what this graph looks like. What does x squared usually look like? Parabola opening up. What does the minus 4 next to the x squared do? Okay. And then if you want to know the absolute value, well, what does absolute value do? So the stuff that was positive stays positive, and the stuff that was negative, what happens to it? It becomes positive. So something like that. So I would say he's concave down right here, and oh no, that would be concave up, sorry. He's concave down right here. So that's from what to what? What do you think this x value is? Okay. Negative 2 and 2. So he's concave down from negative 2 to 2. These would be slightly concave up, just like these are concave up. Okay, and where is the function decreasing? Negative infinity to 2? Okay. Negative infinity to negative 2, it's decreasing. And then again at 0 to 2. So this question wanted to know when is it concave down, this, and decreasing, this. So we have to figure out where that happens both of the time. So this one doesn't match up with this at all. Negative 2 to 2, 0 to 2, which one of those is more exclusive? So I would go with 0 to 2. Is that one of your answer choices? So again, you don't have to write an absolute value function as a piecewise function, even though you should have learned that in pre-cal, but that's the only way to do it algebraically. I know there's 2 or 3 of these on this handout where you really have to think of them graphically because of these absolute value. But if you know what the graph looks like, and absolute value just makes everything positive, stuff that's positive stays positive, stuff that was negative, make it become positive. And then just use the graph to answer where it's decreasing and concave down. Okay, so again, I know there's a couple more like that, and I don't mind taking that type of question again, but before I do that, is there a different type that you struggle with?
Number 8, which is on the second page, and it's the second one down.
This one?
Yes.
Okay, this one looks a little bit tougher. So, if you didn't need help with the last one, glance at your page real quick, make sure you have this as 8, and make sure you're confident with your answer before you tune out here. Okay, so to even know what to do here, you need to be thinking about what you're trying to find. So when it's increasing, do I need to know, should I be using the function, the first derivative, or the second derivative?
First
so where the first derivative is positive. If I want to know concave up, concave down, is that function first derivative or second derivative?
Second derivative.
Okay. So it sounds like at some point I'm going to need to know the first and second derivative to answer this question. So this just looks like a harder derivative to take, but it's not something that we should not be able to do. You're going to have to use product rule here. There's no way for you to rewrite this or distribute this. It's x times some stuff, so you have to do product rule. So the derivative of x with the square root of x plus 3 left alone, plus then x left alone times the derivative of the square root of x plus 3. So you'd have to bring the power down, lower the power by 1, consider chain rule, but there wouldn't be a chain rule in this question. Okay, so that's what I think the first derivative looks like. Now, if realistically though, if I'm going to use this, if I want to know when this is greater than 0, I really need to know, nobody said anything about it, but critical numbers. Critical numbers are where it might be changing directions, so I really need to know when does this equal 0 or undefined. And as is, this is a problem. It's easy to know when something's equal to 0 or undefined if it's one big fraction, because 0 would be when the numerator is 0 and when the denominator is 0, it's undefined. But like this is a problem. So I would take one more step and I would get a common denominator here of 2 square root of x plus 3, so I could shove these things together. So there's a plus x. This guy already has the correct denominator, so I don't want to change the second fraction, leaving him alone. But this denominator needs to be multiplied by 2 square root of x plus 3, and so I have to multiply the numerator by 2 square root of x plus 3. Okay, now that this guy has the correct common denominator, I'll multiply these two things together. This would be 2 times the square root of x plus 3 times the square root of x plus 3, which would end up becoming what? 3x?
Oh, 2x plus 6.
2x plus 6. So, square root of x plus 3 times square root of x plus 3 would be x plus 3, but then you have the 2 times. So, and then just for my own sanity here, I'm going to go ahead and combine like terms and call this 3x. Okay, so I can answer this part. I'm close to answering this part of the question now. When is it increasing? Well, it might be changing direction at critical numbers. So critical numbers are when the first derivative is 0 or undefined. So are you okay with -2 and -3 being the critical numbers? Mm-hmm. Okay, so to help me organize this, when x is -3, we have the critical number. When x is -2, we have the critical number. Now again, part of why we did that handout before this one is I know you guys can do the process of finding critical numbers, but that's almost not helpful if you don't know when to do that. Critical numbers are the places it might be changing direction, so I'm using this as a tool because I really only have to know what's it doing here, here, and here. Those are the only 2 times it changes direction, so at most I need to know those 3 intervals. So I could try plugging in 0 into the first derivative to see that I get a positive over a positive, which is positive, increasing. I could try throwing in like -4 into the first derivative to see I get a negative over a, what's, okay, and imaginaries don't show up on a graph, so this graph probably doesn't exist left of -3. Imaginary number, we don't graph imaginary numbers unless you do something different than an XY plane, but we don't do that in CaliB. And then this one's a little tough, but something between -2 and -3. Like -2.5. This would be negative over positive, which is negative. So for the first part of the question, where is it decreasing? Looks like it's decreasing from -3 to -2. Oh, it says increasing, thank you. Which would be -2 to infinity. That should be the only time that graph's going up. Okay, you okay with that? So, again, keep in mind, I know that some of these questions start asking for 2 parts, but you did this part on other questions. The only thing that gets harder about this is sometimes the derivative is messier, like product rule, quotient rule. Not every time, but when we've got to do it, we've got to do it. And then if you need to know when this equals 0, if you've got 2 terms here, it's pretty common that you need to get a common denominator to write it as one big term. That way it's easy to solve where it equals 0 and easy to solve where it's undefined. Now, for the second half of this question, I need to know when is it concave up, which is a application of second derivative. So here's my first derivative. So to take the derivative of that, I would need the quotient rule. So take the derivative of the numerator times the denominator left alone, and then minus. Yesterday I was helping somebody doing this and they had a plus there, and that was their only mistake. I think it was this exact question too. Minus the numerator left alone okay. Let me go check that out.
What was it?
I don't know, nobody's out there. I'll send an email so they'll check the security camera. Just 9 o'clock. Okay, let's finish this one up. I know it's a longer question, but so I was doing the second derivative. Quotient rule, leave the numerator alone, take the derivative of the denominator. So bring the power down. The 1/2 cancels out with the 2. Lower the power by 1. So if this was a 1/2, now this would be a negative 1/2. Okay, I think that's okay. Does that match up with what you had on the second derivative, or it is? Okay. Now, I don't know if anybody did this, but I know there's a temptation to want to move this to the denominator. You can't do that, or you shouldn't do that. If you move this to the denominator, all of a sudden, instead of just really supposed to be under this, if you move it down here, you're now saying it's under this, which isn't true. This doesn't have this, so you shouldn't put it down here. It's not supposed to be part of its denominator. Okay, and I'm going to run out of space here. So I'm going to rewrite this, though, as over that. Again, you can move it to its denominator, just not this denominator. This denominator would put it under there as well. Okay, so now we've got a complex fraction. We've got a denominator, or a smaller fraction within a bigger fraction. So I really want to multiply this by the square root of x plus 3 to make those cancel. So I'd have to multiply this by the square root of x plus 3, which is actually not that big of a deal because I've got 6 and then 2 of those. So 6 times x plus 3. Over here, these two cancel, and I'm left with a minus 3x minus 6. And all of that is over this stuff. And personally, before I try to use it, I'm going to clean this up and at least combine like terms. Okay, so I believe that should be okay. We're on the same page there?
Do you have to multiply the column by the square root of x plus 3 as well?
Did I not? Yeah, you do. Okay, now are we okay? Okay, so all of that, again, second derivative is not always as difficult, but if we don't practice it, then we can't use it when we need it. But really all of this was for me to try to figure out where it's concave up. So, bless you. The same way that critical numbers are the only place the graph might be changing directions, inflection points are the only place where the function is changing concavity. And potential inflection points come from when the second derivative equals 0, which would be negative 4. And where the denominator equals 0, which would be negative 3. So these are maybe inflection points. You really need to make a habit out of that because inflection points and critical numbers sound very, very similar. One's first derivative, one's second derivative. But one big difference is critical numbers are critical numbers as long as they make the first derivative 0 or undefined. Inflection points are numbers that make the second derivative 0 or undefined and make the concavity change. So if we try plugging in 0, these are the only places that the concavity might be changing. So we can plug in 0. To see we get positive over positive. When the second derivative is positive, it's concave up. We could test the concavity at negative 5 by plugging in negative 5 into the second derivative. We would get a negative over an imaginary. So he doesn't exist left of negative 4, which makes sense with up here. We said the graph didn't exist left than negative 3 earlier, so of course the graph should not exist left than negative 4 either. And then between these two, plugging in negative 3.5 would give me a positive over an imaginary. So imaginary is not going to show up on the graph. So looks like it's concave up from negative 3 to infinity. But for both, if this is where it's concave up, this is where it's increasing. Which one of these is more exclusive? Okay, so they were doing both at the same time. Negative 2 to infinity is what I'd go with. Now, as much as I tried to keep my work nice and neat here, I still think that's one of the biggest challenges to not make a mistake. So, does that match up with any of the answers? This one? Does that look okay?
Yes.
So again, that's on the harder side, but of course you guys need to know all of this stuff. If you want to know increasing, find critical numbers, test around critical numbers. It's increasing when the first derivative is positive. You want to know when it's concave up, you've got to find possible inflection points, which is when the second derivative is 0 or undefined. So you have to find the second derivative, solve to where it's 0 or undefined, and test the concavity around that. And then for these, they want to know both. So Okay, let's do one more. Somebody who's not asked one yet. Give you a chance before others ask a second.
Number 9.
Okay, which one is 9?
It's,
Oh, I should know that, shouldn't I? If this is 8, this one should be 9. Okay, so what intervals is this decreasing? So again, like I've been preaching to you guys since we started this semester, it's fine to think the last question's hard. It's fine to think that it's hard to do that many steps without an arithmetic mistake. It's hard for me, and I've been doing it for a long time. What's not okay is when you read this, you should instantly know what it is you need and how to go about it. You should know the plan for this question. This is not like related rates where you just kind of have to dive into it and it might end up being a short question or a long question. When is a function going to be decreasing? First derivative is, I know. More specifically, when the first derivative is, it's not decreasing if f prime is 0. When it's negative. When the first derivative is negative, it's like the slope is negative. So for this question, we only need to know the first derivative. So this has to be product rule, unfortunately. Derivative of the first term with the second term left alone, plus the derivative of the second term with the first term left alone, since those are both e to the x's. Or this is e to the x, that's an easy derivative. Now, to know when it's decreasing, again, you're not ready for a line chart yet because you don't want to just throw out random x values. You want to test numbers around the critical numbers because critical numbers are the only place where the function might be changing directions. So we need to figure out when this guy is 0 or undefined. So to be undefined, you would need x's in the denominator somewhere. To equal 0, you could factor out an e to the x. You could set each of these equal to 0. Okay, when does e to the x equal 0? It doesn't, that's correct. Either you know what an exponential function looks like graphically to see that he never equals 0, or algebraically you could try to take the natural log of both sides, but you can't take the log of a 0. So this doesn't give us anything to work with. And then over here we could factor out an x. This equals 0 at 0 and -2. So the justification we would want for an FRQ is to see that you know -2 is a critical number, 0 is a critical number. Even if it doesn't change direction, those are still critical numbers. And these are the only places it might be changing direction. So let's see what it's doing at -1. If I want to know increasing, decreasing, I'm looking at first derivative. So if I plug in a -1, this is positive times, this would be positive, this would be negative, -2 plus 1 would be negative. Positive times a negative is negative. Oops. And when the first derivative is negative, it's decreasing. Try something to the right of 1, or 0, like maybe 1. This would be positive times a positive, which would be increasing. And this is the only other place it might be changing directions, so I need to see what's going on over here at like maybe -3. At -3, I would get a positive times a positive, which would be positive. So you don't have to be as careful to get it down to an exact number, but you need to be careful enough to know that it's positive or negative. So where is it decreasing? Now I can see that it is decreasing from here to here. So -2 to 0 is what I'm going to hope is one of our answer choices. Yep, and that matches up. Okay, so I do want to move on, but again, I know most of the rest of those are worked out. There's only like 3 of them that were not worked out, so hopefully you guys have some of those, but I do want you to spend some more time on that if you did not get finished. Okay, let's move over. I would like to look at some of these FRQs today. So we've got 3 on the front that are all no calculator, 1 on the back that's no calculator, and 1 is considered calculator neutral. So I don't think the first 3 are necessarily easier, but they are algebraic ones, and you've had a little more practice with that. You've not had practice, as far as I know, working out ones with this type of graph. So this, no, you have, just not a lot. So to me, 1, 2, and 3 are kind of similar, and then 4 and 5 are kind of similar. So I don't have a preference, but I think we should look at number 4 or number 5 together to do a graphing one. So which one of those 2 looks like the one that you would struggle with the most? I'm going to do that one. Yeah. Number 4. Okay. He already picked it, so let's look at this one. Okay, so first off, read the directions, and then read question A. Okay, so one thing that you need to be very careful about is this guy a function? Is this graph a function?
Yeah. Yes.
No. It is the f prime. It's the derivative. That makes a big difference. Just like working with the function versus the first derivative algebraically, same thing graphically. You need to be aware this is not a function graph. This isn't a relative max, this isn't a relative min, this isn't a relative max. That's not what this is saying. This is showing us the slope of the function. Okay, name the values for which x has a relative min. So look at that, and for part A, put down what you think your best guess would be. Okay, there should be one relative min, and where do you guys think it is? Very good. How did you know x equals 0 was a relative min?
The function goes from having a negative slope to a positive slope. So it goes from below the graph to above the graph.
Okay, so what you're saying is absolutely correct, but this is why we need to practice FRQs. She said because the function goes from, you said this, Okay, that's true. The function does go from a negative slope to a positive slope. That doesn't work for your justification though, because you don't know anything about the function. How do you know that about a function if we didn't tell you anything about the function? So your justification, you can't refer to the, you should not say the graph, you should not say it, and you should not say the function. You should say something about the first derivative. So what's happening with the first derivative that makes that a minimum?
Goes from negative to positive.
Very good. The first derivative goes from negative to positive. So again, it's not that this is saying something different, it's just that, and I know there's that temptation. First off, you guys like to use the word it, don't use the word it. Say what you're talking about. But you can't refer to the second derivative if we don't tell you anything about the second derivative. You can't refer to the function if we don't tell you anything about the function. Your justification has to be based off the stuff that's given to you. Okay, and then this is worth 2 points. This was worth 1, and this is worth 1. Okay, so read B and put pencil to paper, write down what you think the answer is. You can correct it if you need to, but force yourself to commit to an answer. And then I will ask you to share that. Someone besides Harper, since she did the first one. And then we'll kind of pick up speed, and then I'll help you fill in the gaps for the ones that you struggle with. Okay, so this guy is increasing at an infinite number of times, so we can't just say when x is this, 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 this. We have to give an interval. So somebody want to take a guess on when you think the function is increasing? Okay, very good. He is correct. And it looks like they awarded, I don't think these are actual real AP examples. These are made up by our textbook company, but they're pretty similar to the real thing. So they would say to award 1 point for that. And why is that the correct answer? The first derivative is positive or greater than 0. That is all you have to say. But again, don't say it is positive. As much as I want to assume you know what you're talking about, I can't make that assumption. Also, please don't say the graph. The graph of what? Now, if you said the provided graph, well, you couldn't say the provided graph is greater than 0. That wouldn't make sense. But if you said the provided graph, I guess that's kind of the same thing as saying this, but try not to even say the graph. Say the function if you mean the function. Say the first derivative if you mean the first derivative. Say the second derivative if you mean the second derivative. Now, isn't that one, don't you kind of like that better on this? Compared to the circuit and finding the first derivative, finding the critical numbers, testing around the critical numbers. This was more like 5 seconds of work. If you know when it's increasing, you just looked at where the graph was positive, above the x-axis. Bless you. Okay, read part C and commit yourself to an answer. Again, it's perfectly fine to have to erase it and change it, but it's good for you to see if your gut instinct is correct or not. I'm going to put down an incorrect answer here, but I want you to tell me what you think I'm thinking about. Okay, why do you think someone may put that down as a concave down answer? Okay, so if someone did this, they're assuming the graph is the original function, right? Not the first derivative. Because it looks like he's concave down here and he's concave down here, right? But again, this is not the function, which is why that's not the case where that's that. So on that organizing information, when is f concave down? Okay, when the second derivative is negative. How am I supposed to get information about the second derivative out of the first derivative? Good. You have to remember that the slope of f prime is how you get information about f double prime. So this is going to be, well, we'll worry about the justification later. It's going to be concave down when the slope is negative from about here to here. So what if I said -2 to -1, and then from here to here? So what if I say 1 to infinity? That's still not good enough.
So you have the inflection points.
Okay, where did I have them?
It was given.
Right, in the directions. This isn't -1, this is -0.8. We shouldn't be making estimations here. This is -0.8. And over here, this wasn't 1, this was 1.3. That's why that information was in that graph. Yes?
Why are there 3 parts after
I'm sorry?
that? It says 0.8. Not the first derivative.
This is the second derivative.
There are 3 parts after that.
I think that's a printing error.
I still don't know what you're looking at.
It kind of looks like on the second derivative, -0.8. It looks like there's 3 tick marks instead of 2.
So it'd be the third derivative of -0.8.
Oh.
But I think that's a printing error.
Yeah, that's a printing error. I'm sorry. That should be second derivative. Sorry, I never noticed that. Okay, are you guys okay with these intervals, where they're coming from, and how I need to look for that? Okay, now we still need to justify how this is our answer. So, I got these numbers. Concave down is when the second derivative is negative. But again, this is not enough of a justification, because they told me something about first derivative, and this is true because of the second derivative, but how did I know this about this? So we could also say, like, another way to talk about the slope of f prime would be to say that f prime is decreasing during those times. When f prime is decreasing, that's the same thing as saying the second derivative is negative. This is the one that they want, because this is first derivative. Your justification should reflect based on
You don't have to justify your inflection points, because it gave it to you.
sorry?
You don't have to justify the inflection points, because they were given.
I mean, like, I didn't have to justify these either.
Oh, yeah.
I mean, I'm explaining why I think this answers the question, but here's why I think this is the answer to the question. Justification is fine. Okay, and then finally, try part D. Read it, see if you know what in the world it's talking about, and put some thought on to whether you think it's positive or negative. Oh, I didn't talk about the point values from part C. This one gave 2 points for the answer, so 1 point per interval, and then 1 point for the justification. Okay, part D is going to give you 1 point if you can figure out whether it's positive or negative. So worst case, you got a coin flip there. Anybody confident in which one they think it is? What do you think?
Yes, negative.
It is negative. So in this case, you could actually get 1 point even if you weren't confident. Okay, why do you think it's negative? Or anybody who got negative, why do you think it's negative?
Because f of 0.5 is positive,
How do you know that?
according to the provided graph.
F of negative 0.5 is positive, like here? First off, that looks negative, and second of all, this is talking about the function, this is talking about the first derivative. So if you're looking at points on this, that might be steering you wrong. What do you think? Okay, hold on. So she recognized that this was half of mean value theorem. Mean value theorem says instantaneous rate of change is equal to average rate of change. Is this the instantaneous rate of change or the average rate of change? Okay, average rate of change, correct. Okay, what else were you going to say?
Right, since the slope from, what you're looking at here is the average slope from negative 0.5 to 0, which is negative.
Okay, so do you guys see how this one's under the x-axis, so we know that this is negative? If the instantaneous rate of change during that time is negative, mean value theorem says that the average rate of change has to be negative as well, right? So that's how I know that at this time, during all of this time, the instantaneous rate of change is negative. Mean value theorem tells us that the average rate of change would be equal to that. Thank you. So their justification was mean value theorem can be applied since the derivative is negative during these times. And the derivative is the instantaneous rate of change. So if the instantaneous rate of change during that time is negative, then the average rate of change is negative, which is what that is. Now again, notice they didn't give you a hint to think about mean value theorem. You have to recognize the mean value theorem well enough to realize that that is part of that. And you don't know what f of 0 is. You don't know what f of negative 0.5 is because you don't know what the function is. But we still know enough to know that it's negative. Instantaneous rate of change that whole time is negative, so average rate of change during that whole time is negative because of mean value theorem. But this does force you, I like these type of questions because you can see at least parts A, B, and C. Honestly, if you know what you're looking for on these, those can be very quick questions. Now D, I don't know, you've probably never seen one like that. You'd probably spend some time thinking about it, and then you're going to make that mean value theorem connection or you're not. But to me, this is a little bit nicer than having to do it the algebraic way. Okay, and then justification was the 9th point. So you will see this type of stuff again, whether it's in our tests, our next test, whether it's a final exam, AP exam. This type of stuff is very common to ask. So part A, relative min. Part B, increasing. Part C, concave down. Or part D, mean value theorem. Any of those you want me to address again?
Can you show us how that's the mean value theorem?
You just have to recognize that this looks like this slope formula, which is the same as average rate of change. And because this is a differentiable function, over the whole thing, that guarantees that it's also continuous. So the conditions for mean value theorem are being met. It's continuous and differentiable during those times. And mean value theorem tells us that the average rate of change, which is this stuff, is equal to the instantaneous rate of change also known as derivative. So this we got from the graph. We can see from the graph that this is negative during those times, which means that the average rate of change, which is this, would have to be negative during those times. So I don't have near enough information to give you a number, but I know it has to be negative. Okay. I'll leave it up to you guys. Do you want to do it one part at a time? Like, I want to do question 5 next. Do y'all want to do it one part at a time and then discuss it on the board, or do you want to go at your own pace and just have me come around and help you when you get stuck? Does anyone have a preference? Yeah. One part at a time. Okay. So part A. So once again, like the last question, these FRQs, someone in my other class has been describing them as impossible. I don't know if I'd go that far, but I understand the sentiment. But they do get much easier, but only with practice. So think about what you learned from part 4. Reading the directions, we got some important points that ended up showing up later in the question that are easy to miss. How to read the graph, the fact that this was a first derivative graph and not a function graph changed how you have to look at it. But read the directions, read part A, and see if you can come up with an answer. Okay, part A. Well, this one's tough. Okay, the answer, anybody come up with -2/3? Okay, so it wants to know f prime of -1. Well, this is the graph of f prime, so they want to know when x is -1, what is the y value? That's what they were asking you for in part A. Now, they didn't tell you what that was in the directions, so how did y'all come up with -2/3 here then?
The only way I can see you did it is you have 3 over and 1 down. And so you know there's going to be it's a straight line.
Okay, straight line.
So you take 1 minus 1 divided by 3 and multiply by 2 because you're going over 2 different spots.
Okay, that's true.
I'm not going to remember that way.
Yeah, so he realized this is a straight line. It sounded like he was doing rise over run to find the slope here. Do you see how it's going down 1, right 3? To get from this point that we're sure is on the graph and this point that we're sure on the graph. So if you go down 1, right 3, down 1, right 3, down 1, right 3, at that rate, that puts that at negative 2/3. So that is 1 point, and I don't know. This one, I don't know that I would honestly know to do this, but they said that the other point came from making this equation. So that can be frustrating because it didn't say to make that equation, but if somewhere in your justification you talked about this line or the slope of this line or the equation of this line, I think you could probably get that point. But you can't just throw down the answer. You need to put some explanation. So if that means you need to write out a sentence or two, fine, but that one was literally just asking for a point on the graph. It just was not a nice whole number, so you had to put some thought into that. Okay. All right, if you've not moved on to part B, then please do.
Do you have to say the interval where that is the equation for f prime of x?
Yes, that would probably be best. From negative 3 to 0. Because that's not really the equation the whole time, of course. Okay, so try B.
I also just didn't do since my school. I did do circumventing rates. Oh wait, that was option 1. Anyway, so yeah, I didn't do 2 of my assignments, and I have a 91 in this class. So I'm like, so I have like a 93 as my test grade average, and 989 as my homework grade, which is really super fun.
They were really bad at first. This is
Really mad. I missed like 1 class, and then I don't know, I'm mad at myself. There was 2 assignments, so she like brought my grade down 10 points. They were. Anyway, I got to look at Well, it's the first derivative is that and then the second derivative is
Okay, that one should have been pretty easy, right? What's the answer? Okay, how did you know that so quickly? Slope.
of the first derivative. That's like. So the way that I justified it was that I took the equation that you wrote for part A, and then I took the second derivative of that, so it was second derivative of x equals negative 1/3, and then I said second derivative of negative 1 equals 1/3, or negative 1/3. Is that valid?
That's fine.
Okay.
But you're kind of going in a roundabout way, because where did we come up with this?
Yeah.
Like, we thought about the slope of this to get that originally, so I think this is plenty fine. This one was only worth 1 point though. 1 point if you figured out it was negative 1/3. Second derivative is the slope of the first derivative. That's the only way you're going to have information about the second derivative. Okay, if you've not started looking at part C yet, go ahead and read that and see what you would try.
Just do negative.
Okay, anybody got an idea of what you think the inflection point might be? Okay, so where do inflection points come from? Okay, and how are we going to get information about the second derivative from the first derivative? Slope. Okay, so we need to be thinking about slopes of this. Okay, so more specifically, inflection points have to do with the second derivative, but what about the second derivative?
With the second derivative equal to 0.
Or, okay, where would the second derivative be 0 or undefined in this?
Negative 4.
Okay, I agree. At -4, the slope of the first derivative is 0, which means the second derivative is 0. There's another inflection point.
Is it 1?
At x equals 1, I agree. What's the second derivative here?
Is it like a cusp? So you can-
Right. You can't take a derivative at a cusp. So if the derivative of the first derivative is undefined, that means the second derivative is undefined, and that is one way to find inflection points. So where's the other one that's like that?
0.
0. So, if you really know, inflection points are when the second derivative is 0 or undefined, and you know that the second derivative information comes from the slope of the first derivative. Here's where the first derivative is 0. Here's where the slope of the first derivative is 0. Slope of the first derivative is undefined. There's 3 times. So, for our justifications here, it looks like 0 and 1 were for one reason. This would be when the let's say the second derivative is undefined because the slope of the first derivative is undefined. Same thing. But for -4, it was because the slope of the first derivative was 0, which meant that the second derivative was 0. We need 2 justifications there. Yeah.
Why isn't -3 also?
Well, because this is, you're correct. The first derivative doesn't have a slope here, so the second derivative is undefined. But since this slope is negative, that means the second derivative is negative, and so this is concave down. And then from here to here, the slope is still negative, so it's still concave down. If the concavity is not changing, then it's not an inflection point. So you're correct that we should have considered that, though. Okay, this one just gave out 3 points, so based on how it wrote it, I think you just get, it wasn't based on justification at all, but however many of those 3 you could come up with is 3 of the points you got.
So if it doesn't say justify in the question, do you justify it?
I would still justify. Because obviously I'm never going to try to cheat you guys, but we always grade based on the rubric, and like this part A, I almost feel like expecting this is almost unfair, but sometimes they're like that. Sometimes they expect you to say things that they don't point out very well, so I would always justify personally. Okay, one more, and then I'll ask you to do one of the others on the front page, but I will let you pick and choose. But okay, so read D, see if you can figure out what the question's like and what you would do to start it off. Notice this is a no calculator question. Okay, if I would like to know if g of x, which is some made up function, is increasing or decreasing, what do I need to consider? Okay, if the derivative of g is positive, we can say it's increasing. If the derivative of g is negative, we can say it's decreasing. First derivative is increasing, decreasing stuff. So, when I take the derivative of g, well, what's the derivative of f? Okay. What's the derivative of sine squared?
2 cosine.
Maybe. Okay, so bring the power down, lower the power by 1, and then chain rule times the cosine. But we would like to know specifically at negative pi over 4. So everywhere there's an x, we're going to replace with a negative pi over 4. Okay, this is going to have to come out of the graph. Because this is f prime. And what is negative pi over 4 as a decimal? Like, where should I be looking at on this graph?
About 3/4.
Okay, so somewhere between 0 and...
Or negative 3/4.
Yeah, negative 1 and 0. Everybody okay with that? It's somewhere in here. So, we don't know what that is, but we know that this is negative. This is negative. Hold on, let me restart that. We know that's negative something. Okay, over here, we've got 2 times the sine of negative pi over 4. So this is a unit circle question. What is the sine value at negative pi over 4? Okay, and then the cosine of negative pi over 4. Okay, so if this is something negative that I see from the graph, and you see how when we multiply this stuff together, we get something negative as well, that means that I can't tell you numerically what this is, but this is negative. So the answer to the question is what? Decreasing. Okay, and point values there, looks like they give 1 for the derivative. You need to be careful with chain rule there. If you don't like the way sine squared is written, remember you can rewrite that. This is the same thing as this. I feel like you're more likely to remember chain rule like this, but this is how we write trig functions. 1 point for that. 1 point for the answer, so that would be this, and 1 point for the justification. And the only justification they expected there was this part, saying that it was negative. Okay, any clarifying questions you'd like to ask about this one? Any parts of this, number 5?
Do you have to box every answer you want them to get for, like box every part of?
You don't have to box your answers, but sometimes it's nice because like if you do some work and you do this and then later you do this and you don't specify like which one you think is the answer, I can't assume that you know the right one is the answer. So sometimes y'all do that, and that's where it helps if you box it in. I can assume that.
I just meant like the derivative and.
Oh, no.
I mean, obviously I would say decreasing, but.
You don't have to box it in, but you'd have to say something about that to get the justification point.
Okay.
No, I'm just trying to circle to help you highlight the stuff that they're expecting to see. Okay, so on the front page then, there are 3 that are algebraic approaches. They're all no calculator. I hope to have enough time to ask you to do all of those because again, the sooner you get a lot of FRQ practice under your belt, the sooner you're going to feel about these, or feel better about FRQs, not just this unit, but just for the year as a whole. But based on how much class time there is, I'm going to ask that you just pick out one of those. So if you want to read questions 1, 2, and 3, make a choice about, if I was you, I would do the one that you think is the hardest personally. That's going to be the one that you have the most to learn from. And if you pick number 2 or number 3, I have those worked out on my website. So if you get stuck on those, you can use those to get unstuck. I don't have the first one, but you're still welcome to do the first one if you'd like. But I'd like you to feel pretty good about one of those 3. So pick whichever one you want. But when you get stuck on it, actually put a good effort on trying to squeeze out all of the points. And then I guess if you didn't finish the circuit or don't have the circuit finished, please work on finishing that up as well. It depends on what it is. There's only 4 minutes, so.
Number 12, it's one of the absolute minimum value. It doesn't look like it'll take too long.
Which one is it?
It's the, on the last page, the second spot.
Don't look at that. Okay, so absolute value. So what does natural log of x look like?
Oh, you're putting this back? Or, no, I'm just saying, like, would it be the same thing?
Okay, y'all are supposed to know this. It goes through x equals 1 and does this. All logarithm graphs without transformations look like that. Whether it's base e, base 10, base 3, base 5, whatever. They all look like that. What does absolute value sign do? Okay, so stuff that was positive stays positive. Stuff that was negative becomes positive. So the absolute minimum occurs when x equals what? Right there. I would just do it from a visual standpoint. But you do need to know what a logarithm graph looks like. So. Well, obviously you did not. You were supposed to.
You were my teacher.
You were supposed to.
Have you put a place on Google Classroom for people?
I don't think I have. I will definitely pick it up for points, but I know some people are still working on it, so. Also, so the door slamming was just a random incident. They did identify the student, and they'll be seeing an administrator before the end of the day. So, just somebody being silly. Nope.